Alright, it's time to really start doing a more in-depth examination of the force of gravity. So we know that gravity, or the force due to gravity, is going to affect every single mass in the universe. It doesn't matter where you are located. As long as you are dealing with any two masses, there will be a force of gravity between them no matter how close or how far apart they are. And as we said, if you exert a force of gravity on an object, that object will also exert that same force of gravity back on you, equal in magnitude, opposite in direction, once again as a consequence of Newton's third law. So we just kind of want to do a little bit hand-wavy arguments for a second. So Newton hypothesized if you had two objects with mass 1 and mass 2, Newton theorized that the force of gravity, it should be proportional to that product of two masses. So we can say that Fg is proportional to m1 times m2. We also saw last that the gravitational field strength is proportional to 1 over r squared, so we have that inverse squared relationship. We also said that if the gravitational field strength is proportional to 1 over r squared, Fg itself is going to be proportional to 1 over r squared, because we want to recall that the gravitational field strength is directly proportional to Fg. So if they're directly proportional, they are both going to be proportional to 1 over r squared. We can kind of see that in our little diagram here. Like, on Earth, we have this object on Earth, so it has a force of gravity Fg acting on it. So we move it to a distance of twice Earth's radii. The force is now a quarter. We move it to 3 Earth radii. It's now 1/9. We could keep going, and it'd be 1/16th, 1/25th, so on and so forth. So this is just meant to show the inverse characteristic of the force due to gravity. So what we're going to do is we're going to combine those two relationships. We're going to combine that Fg is proportional to the product of the masses, and Fg is proportional to 1 over r squared, and we get this lovely looking thing. Now, when we talked about Newton's second law, we talked about a proportionality is good to kind of give us that idea of how the relationships work together, but we can't say Fg equals something without that constant of proportionality, that constant that links both of these sides. Well, the constant that links both sides is going to be this uppercase G. Sometimes, like colloquially, we'll refer to it as kind of like big G, and that's what I'll usually refer to it as, big G, just to distinguish it from little g, or like the gravitational field strength or acceleration due to gravity. So this big G, this is what we call the universal gravitational constant. So the value of big G, it is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So it's quite a mouthful on the units. This constant, please do not memorize it. It is located on your data sheet under the constants section. So this constant, it's valid anywhere in the universe, hence the name universal gravitational constant. So what that's going to do is that's going to give us a formula to determine the gravitational force between two objects. So we have this Fg equals G m1 m2 divided by r squared. So you'll notice Fg, I have these bars, these vertical bars around them. That's telling us that for this, we're looking strictly at magnitude. So Fg is going to be the magnitude of my force of gravity, that's in newtons. Big G is that universal gravitational constant. Again, that's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We got m1 and m2. These are the masses of the two objects that are interacting with one another. They're both in kilograms. And then r is that distance between the centers of the two masses. So if I have kind of a mass here, and I kind of have a mass here, we have the two centers. That line that joins the centers of these two objects here, that's the distance that I'm going to call r. And you'll kind of see that relationship coming up, that distance between the centers, when you do Physics 30 and Coulomb's law. R is a little bit of a bad choice for variable because we like to think a lot about radius, but it's actually more of a distance. And for the most part, you will be given that distance between the centers of the objects. Will kind of trick you when we do stuff with altitude, but I'll talk more about that later. And then that r is, as we said, that distance between the centers of the two masses in meters. So this equation, this Fg equals G m1 m2 over r squared, this is known as Newton's law of universal gravitation. Now you might say, well, Mr. O'Donnell, we already learned that Fg equals mg. That's correct, but that only works if you know what little g is. On the surface of the Earth, we know little g is 9.81 newtons per kilogram. But if I move you to another planet, like let's say Venus or Mars or Jupiter or Saturn, we don't know what little g is on the surface of those. So Fg equals mg is not going to work. This is more general. Fg equals mg comes from this equation, but we'll talk about that a little bit more later. Now, as I've said before, and it's always worth repeating because students always get this technicality incorrect, when the two objects are interacting, keep in mind that the magnitudes of their force as they exert each other are the same as a consequence of Newton's third law. They're just acting in opposite directions. And that force, that acts along that line that joins the two centers of the masses. So here's that line that joins the two centers. So as I've said, we call that distance r. Now I have mass 1 and mass 2. So mass 2 is going to try and attract mass 1 towards it. So we have this force of 2 acting on 1, pulling m1 towards m2. At the same time, we have this force of mass 1 acting on mass 2 to try and pull mass 2 towards it. So these two forces, F21 and F12, they are equal in magnitude. They are just opposite in direction. So we just say F21 is equal to the negative of F12. Again, consequence of Newton's third law. And all these experiments have shown that the magnitude of the gravitational force, it doesn't actually depend on the medium where the objects are located. So the force of gravity, say, between myself and this pen that I'm writing with, it's going to be the same as it is in this room, as it is under the sea, as it is out in space. The medium does not dictate the force of gravity. So let's look at a couple of examples of Newton's law of universal gravitation. It's not meant to be an overly complex equation. So let's see what we got here. So we want to determine the magnitude of the force of gravity. So again, we're just focusing on magnitude. So between myself, we'll say mass 110, and some unsuspecting student with a mass of 60 kilos, and we're separated by 200 centimeters. So we have our equation for the magnitude of the force of gravity. So we have this g mass 1 mass 2 over r squared. So main thing here, r only works when it's in meters, so we don't want 200 centimeters. We'd like that in meters. So for this magnitude, we have big G, that's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We have my mass of 110 kilos. We're going to have this unsuspecting student's mass of 60 kilos, and then we're going to divide that by that 2 meters, and then squared. Now, my young friends, this is a mistake that almost every student makes at one point in their physics career, and it's like getting fish in a barrel. A lot of students, they'll write that square there in their equation, but they'll forget it when they're actually calculating it. So that is probably one of the biggest mistakes that's made. And on exams, if it's a multiple choice, we always have an option ready where a student forgets that square. Do not forget to square your R value. That's really important, and I swear we catch a lot of students on that. So if we remember our square, we're very careful with our calculations. So we're going to have force of about 1.10 times 10 to the minus 7 newtons. So that's my magnitude of the force of gravity. It's not very large, but as I said, regular people, they don't produce very large forces of gravity because they're not very big. Like, I'm a big guy, but I'm not big enough to produce a really large gravitational field. So it is what it is. So yeah, that force, not very big. We're not going to start pulling people together right away here. Now, last one, because we always like to have a little bit of rearrangements, because it's always fun. So let's look at the force of gravity between two people. They both have a mass of 75 kilos, and the force of gravity between them, or the magnitude of it's 1.50 times 10 to the minus 7 newtons. So we're going to determine that distance between the two of these people. Well, once again, we can write out our equation. So we know that Fg is g m1 m2 over r squared. So our objective this time, we'd like r, but we're going to have to get at least r squared first. Since it's in the denominator, we'd like to bring it up top. So we're going to multiply both sides by r squared. That's going to get rid of that here. So on the left side, I'm going to get this Fg times r squared is g m1 m2. Now, I have r squared up top. I can isolate for it. I don't want that Fg on the left there, so I'm going to divide both sides by this force of gravity. So what I'm left with now is I'm left with this nice little equation. I have this r squared equals this g m1 m2 divided by the magnitude of the force of gravity. Well, that's all well and good, but again, I want r, not r squared. So last thing, we're just going to take the square root of both sides. So what that's going to give us is that is going to give us our equation for this distance between the two people. So it's going to be the square root of g m1 m2 divided by the force of gravity. So these are also common questions ask you to solve for r. Biggest mistake usually happens in rearranging, like people forget to bring that r squared up top first. So usually people will have the square root of fg over g m1 m2. If you get that, you didn't isolate for r squared properly. So now that we have our formula, let's plug stuff in. So we got this 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Each person has a mass of 75 kilos, so we got 75 times 75, and then we're dividing that by this magnitude of the force of gravity, and then we're going to square root that whole thing. Now, with all these questions, if your answer seems a little funny, your gut's telling you something's wrong, trust in your gut. Your gut's usually fairly right on a lot of these things. Now, if I do this, let's see what I'm getting here. So I am getting, a very, I know why. In my calculator, I forgot to put 10 to the minus 11. I was going to say, this is telling me that the people are 500 kilometers apart. That's a little bit too much. So good lesson to give you on that one. I got an answer that seemed a little funny. Went back to my calculator, noticed I forgot to put the 10 to the minus 11. So again, if your answer seems odd, your gut's telling you something's wrong, trust in your gut. It's pretty good. It's pretty intuitive. All right, answer gets a little bit more sensible. So I'm going to get it's about 1.58 meters. So what that's telling me in this scenario is that the two people that are talking, interacting, whatever they happen to be doing, they are about 1.58 meters apart. Newton's law of universal gravitation. We like to give you these nice simple questions. They're not meant to be hard. They're meant to be quick, simple, build that confidence on the exams.